Hey class, it's Mr. Hofstad here with our topic 5 continuation. Our previous lesson covered voltage and current. Today we'll look at resistance and how it's really closely and importantly tied in with voltage and current. So resistance measures how difficult it is for current to flow. It's also measured in ohms. That's a good starting point, but let's go a little bit deeper. So resistance will be found in anything where current is passing through. It just depends how much resistance there is. It's very similar to friction. It's essentially the friction experienced by the electrons as they travel through any current carrying conductor, right? So if it is a good conductor like copper, there's going to be very little resistance, and we'll have the electrons just passing by nice and easily. Whereas if it's something a little bit less conductive, maybe even something like wood, then our electrons aren't going to be able to move as freely. They're going to experience more friction as they're passing through that. There's less room for the electrons to pass through. A whole bunch of factors play into this, but the important thing is that higher resistance means essentially more difficulty for electrons to flow, right? They're going to be colliding with other atoms. They're going to be colliding with the sides of the conductor and with each other more frequently. So resistance can be calculated using Ohm's law. Ohm's law is usually written as voltage is current times resistance, but we can manipulate that to say resistance is equal to voltage divided by current, where voltage is our potential difference or the energy difference between 2 points, right? Usually looking at our cell, the energy difference created by this cell, right? From that chemical energy being converted to electrical energy. So voltage in joules per second, or volts, joules per coulomb, which is a volt. And we're dividing that volt by our current, which is how many coulombs of our electron carriers are passing every second. So, right, we can measure voltage using a voltmeter. That's what this guy shows. We can measure current flow using an ammeter, which is this guy here. And within this wire itself and each of our lamps or whatever it is we have here, we're going to have a different resistance as well, right? So easiest way to calculate it is just to take a voltage and divide it by a current. Here's an important note for your IB papers next year. The gradient of a voltage current graph is not the resistance, right? They're going to try to trip you up on that, but it's not as simple as that. So if they do show you a voltage current graph, don't fall into the trap of selecting the gradient of this, or the slope. That's the fancy IB word for slope. It's not going to be equal to resistance. Okay, and here we have an ohm and a coulomb. Okay, so if we were actually in class and we actually had access to voltmeters, we could do this easy but informative little lab. So we'll give it a try virtually through this little presentation. So if we take a pencil and really darkly fill in this rectangle, we're actually, with the graphite of the pencil, creating a conductive layer for current to pass through, right? And if we took a multimeter and connected some wires to it, we're able to actually measure the resistance of that graphite drawn onto the paper. different settings, right? Since we're working with something that is pretty highly resistive, we'd set it to something that has a really high resistivity, right? 200,000 ohms resistance rating. Then we're going to use our multimeter to measure the resistance across different lengths of this graphite. Right, so as we increase the length, we're increasing the distance that our electrons or our current would be traveling through this graphite strip. So as we're increasing the length, we should also see an increase in resistance each time. So if you actually perform this right at 1 centimeter, 2 centimeter, going up each time, you could get some really good simple quantitative data, make a nice table, and then graph how the length of the strip is related to the resistance, right? So you could even go all the way up to 20 centimeters, plot the scatter graph, right? Remembering to include each of these points and draw a line of best fit, as this is just experimental data, nothing is perfect. And we should get something that looks like this, where we can see a nice direct proportionality between resistance and the length or the distance between our two nodes. All right, so here I'll let you guys think about this on your own. I'll throw these questions in our Google form for the week, and you guys can give me your thoughts on these 3 questions, right? Thinking about why it happened with what we know about resistance. And if we made it wider instead of longer, how would that change it? This is where we're kind of going into here. So try to answer those questions before you finish the video. If you don't, oh well, a little bit of hints thrown in, but that's not a problem. So resistance is proportional to the length of the wire, right? We just saw that relationship from that graph. And resistance is inversely proportional to the cross-sectional area of the wire. So thinking about the whys of all of these is really important, right? So the longer it has to travel, the more friction you're going to be experiencing as those electrons are traveling through the wire or the whatever conductor, right? Whether that's our graphite strip or some copper wire. So as we increase the length, right, and we're not changing anything else, we're just increasing the amount of friction proportionally, right? So increasing the resistance proportionally to the length. For every centimeter we're adding of length, we're adding on a centimeter's worth of resistance. Whereas when we increase the cross-sectional area, we're actually providing a wider pathway, right? So if we have a really narrow, right, small diameter wire versus a really big one, we're going to have a lot more electrons colliding against each other, against the walls of the wire, lots more friction occurring here. Whereas when we increase the cross-sectional area, right, they're able to flow a lot easier. We're going to have less of that resistance, less of that friction. All right, you can almost think about it like water flowing through a pipe, right? If we have a really narrow pipe, there's going to be much slower flow, right? Higher pressure, all sorts of things, right, related to this increase in resistance. Whereas as soon as we get a larger, wider diameter pipe, water is able to flow much more easily, and we're getting a lot less resistance. And it depends on the type of material, right? This one we kind of need to go into our next slide and understand how different materials can conduct differently. So here is our most complicated formula for resistivity or resistance, right? Where resistance is dependent on the resistivity of the material. So something like copper would have a fairly low resistivity, whereas something like lead or wood would have a much higher resistivity. This measure has to do a lot with the chemistry and the atomic structure of the elements that the material is made out of, and how tightly they're holding onto the electrons, right? If there's a lot of free electrons and there's not much electric force holding onto them, then they're going to be able to flow by much easier, have a lower resistance, right? Whereas when they're holding more tightly, we're going to have a higher resistivity, therefore a higher resistance. So resistance is directly proportional with resistivity, and that's the one that's actually measured in ohm meters. And then we have the length of our conductor, right, how long the wire is, and the cross-sectional area of the conductor in meters squared. So we have ohms, we have meters, so this will be ohm meter times a meter, so we have ohm meters squared on the top, and we have meters squared on the bottom. So all of our meters will cancel out, and we're left with our resistance in ohms. So this is given on your data sheet, but if you ever forget it, you can fall back to our units. All right, nice example for us here. If the resistivity, right? So resistivity would be our rho. That's the little p that we just saw. And it should be in ohm meters. Good, it is. We want to find the resistance of a piece of copper that has a length of 1 meter. So L is here, 1 meter, and a diameter of 0.1 millimeters. So we'll have to find area using pi r squared. So not the most difficult mathematical question you've seen. Everything's given to you. You just have to pull it into the correct units and chug and plug, essentially. Put everything in and calculate it out. So radius of this would be half the diameter. We're going to convert it to meters, so 0.5 times 10 to the negative 5 meters. Pi r squared gives us 7 times 10 to the negative 9 meters squared. Go ahead and use that full value in your calculation rather than the rounded value. Right, we're going to have a couple more decimal places than one significant digit. And then our resistance will be our resistivity, 1.7 times 10 to the negative 8, times our length, which was 1, divided by our area, this guy, giving us 2.42 ohms of resistance. All right, you have a whole bunch of questions now in the homework package. I can even attach it to this week's coursework. Give those a shot. They shouldn't be too crazy. If you do get stuck on any of them, please send me an email. So we can vary the voltage and current using a variable resistor and then plot the graph of the voltage against the current. So here is our symbol for a rheostat, which means that essentially if you think about any dimming light switches or anything like that, that's essentially what we're doing. We're controlling the resistance of a resistor, right? So you can increase it so that hardly any current is able to flow through. We have a really high resistance, or we can decrease it to a point where there's hardly any resistance at all. And that will give us different voltage and different current depending on how much resistance is actually there. So here would be our symbol for a rheostat, and a rheostat most simply put, is just a variable variable resistor. So something where you can vary the resistance, right? You can change how many ohms of resistance this rheostat is applying. Okay, so as the current in the lamp increases, its resistance increases. Let's think about that for a second, right? If we look at the formula, here's the one that we've been working with. Resistance is equal to voltage divided by current. That seems a little bit backwards, doesn't it? It looks like we have an inverse proportionality where the current increase would actually decrease the resistance. But as we increase the current, we're actually altering the voltage. And if you think about it, again, like a tube or a pipe that electrons are flowing through, if we put more current, which means we're throwing more electrons into our pipe. So here's low current. We've got hardly any electrons in it. I for current, versus something that's kind of plugged up with a higher current. So you now have more electrons flowing. We're going to have more collisions between electrons. They're all going to be fighting for space, right? And as we have more of those collisions, we're getting more friction within the wire. So we're actually going to have an increase in resistance. So this formula can be a little deceptive, right? But remember that current and voltage are linked. So as you're increasing the current, right, if you're using the same power supply, right, you're going to have a proportional decrease in voltage, but you're actually going to see, it won't be directly proportional, right? You're going to see the resistance increase because the amount of electrons flowing through are going to be quite a bit higher. Okay, so we don't always have potential difference, right, which is what we usually think of as volts. I don't want a laser pointer, I want a pen. V is not always proportional to current because some materials act with non-ohmic behavior. They don't follow Ohm's law where V is equal to I R. So that's our Ohm's law. So when something is non-ohmic, we no longer have this proportional relationship between voltage and current. So some materials, like this filament lamp shown in this graph here with current versus voltage plotted, don't show a nice straight proportional line. We'll see that as we increase current, as we increase voltage, our current won't increase proportionally, right? It'll kind of dwindle down and eventually flatten out. So some materials are non-ohmic, and different effects like the heat and the intermolecular forces between the atoms within the wire will actually get rid of this proportional relationship between current and voltage, and we'll see this non-proportional relationship instead. So this is what we're more used to seeing, right? And here temperature again plays a big part into it. So as you heat up metals, right, you're adding kinetic energy to them. You're actually changing the resistance within them. You're going to affect the ability of current to flow through them. But if we're keeping it at a constant temperature, right, and where we're just working with a metal wire, right? So copper would be our most common, but we can have other conductors as well. We're going to see this ohmic behavior where voltage is proportional to current because V equals IR, Ohm's law. So Ohm's law means we have to ensure that we have ohmic behavior in order to use it. And you'll see we get this nice perfectly straight line, this direct proportionality between voltage and current. Okay, so this is Ohm's law. Join the resistance, Ohm, funny. When the temperature is kept constant, the current through metallic conductor is proportional to potential difference across it. So there are criteria for this. It needs to be a metal and it needs to be a constant temperature. All right. This is where we're starting to get into the math heavy portion of the unit of the topic. I'll stop before we actually get into the long laborious examples. I'll save that for next week. And we'll just kind of briefly introduce how adding resistors to these circuits kind of affects the math and our circuit analysis. So we talked about current in series, we talked about voltage in series. Now here's resistance in series, and it's very similar to adding voltage or current in series. So when we add resistance, add these resistors, we would call them, in series, right? The total resistance would just be adding up all of the resistors that are in series, one after another, right? Because we're having the same current flowing through them, right? It'll slow down and it'll slow down, or it'll lose energy, decrease its potential difference, its voltage across each resistor until eventually it reaches back up the cell. But as long as they're passing through on the same path, the same pathway, they're in series and they just are simply added together. So that one is very intuitive, straightforward. So if we have 20 and 22, right, we're just going to add them. We have 42 ohms, right? We would add all of these and get 420. All of these, we get 184, right? Just simply adding all of the ones that are on the same pathway in our circuit. All right, resistors in parallel. Unfortunately, we don't have access to this practical right now. I'll see if I get into school, because this is kind of one of the more mind-blowing parts of circuits. When we're adding resistors in parallel with each other, something really weird happens. We are working with a whole bunch of reciprocal values here, and our total resistance will actually decrease as we're adding more resistors to it. So when they're in parallel with each other, more is actually less resistance, right? And if we kind of break this up and think about it, as our current is flowing in, right, our current is going to split half and half, right? And now instead of the full current going through both of these resistors, we have half of the current going through one of them. So they're joining back up here, and they actually still have more energy, a higher voltage than if they would have gone through both of these in series, because only half of them, half of the current is going through each of these, rather than the full current going through two, half the current is going through one. So this is the relationship that we need to remember whenever we're working with resistors in parallel, that the reciprocal, or 1 over the total resistance, is equal to the reciprocal of each resistor added together, right? 1 over R1 plus 1 over R2. So in order to find the total resistance, right, we're going to take the reciprocal, right, add each of the reciprocals together, right? Reciprocal is when I'm saying that, I just mean 1 divided by the value, right? It's our math word for a reciprocal. So we're going to add all the reciprocals together, and then we're going to take the reciprocal of that by finding this answer, taking it and going 1 divided by that answer gives us the actual total resistance. Right, so here as an example, we've got 6 ohm resistors, 3 of them running in parallel. So the total resistance would be 1 over R is equal to 1 over 6 plus 1 over 6 plus 1 over 6. So that would give us 3 over 6 is equal to 1 over our total resistance. But here we're looking for the total resistance, not the reciprocal of it. So we're going to take 1 divided by total resistance, or we're going to flip top and bottom. That's another nice trick for finding the reciprocal. We're going to switch top and bottom on both sides, which is essentially taking this answer 1 divided by this and 1 divided by 3 over 6. Right? So if you're working with fractions, you can just simply switch top and bottom to find the reciprocal. If you're working with decimals, like if I had this as 0.5 instead of 3 over 6, I would then go 1 divided by that answer, 0.5, gives me 2 ohms. So it depends if you prefer working with decimals or with fractions, how you're going to mathematically calculate those reciprocals. Okay, and you can see that if these were in series, we would actually have 18 ohms of resistance, but since we put them in parallel to one another, we're left with actually only 2, which is extremely different. So we can really use this idea of splitting our current up and running them across resistors that are now in parallel to really reduce the resistance of a circuit. Even more complicated, here we have 2 10 ohm resistors. So if we were to do the math for that, right, 1 over R is equal to 1 over 10 plus 1 over 10, which becomes 2 over 10. And if we find the reciprocal of 2 over 10, we get 10 over 2. 10 over 2 is equal to 5. Right, 5 ohms. Right, or we could do 2 over 10 would be 0.2, 1 over. So this is either going to be 10 over 2, or we could calculate it by doing, instead of a fraction, 1 divided by our decimal of 2 over 10, which is 0.2, which gives us 5 ohms. Right, so those two are in parallel, but they are not in parallel with the remainder here. They're actually in series because the current joins back up and continues. So we have the full amount of the current flowing into these 4 10 ohms in parallel. So if we did this again, but instead of having 2 over 10, we have 4 over 10, we end up with 2.5 ohms. So this section here would provide 2.5 ohms of resistance, but it's in series with this other set of 5 ohms in parallel. So we add those two together because these two are in series. So within them, we have them running in parallel, but as you look at them separate, they're actually not in parallel with each other, they're in series with each other. So we add those 5 and 2.5 ohms and we get 7.5 ohms. Yes, ask me difficult questions. I can't wait. All right. How much we got left in us today? Yeah, we can do this. This one's pretty simple. Power is voltage times current, right? Because if we break up their units, this becomes pretty intuitive. Voltage is joules per coulomb. Current is coulombs per second. If you multiply them together, the coulombs will cancel out, and we're left with joules per second, which is a watt and a measure of power. So power is amount of energy per second, energy measured in joules per second, which is a watt. Joules per second equal watt. So in order to calculate the power of a circuit, we need to know the voltage across the entire circuit, right, or a portion of it. If you're looking for the power of this lamp, right, we would just find the voltage across this lamp and the current across that lamp, and we'd get a power by multiplying voltage and current in watts or joules per second. So in resistors and lamps, we're not gaining power, obviously, we're dissipating or losing power. We're consuming energy over time, right? A light bulb isn't generating, it's dissipating, which means it's removing it. So power is equal to voltage times current. We also know that voltage is equal to current times resistance, which is Ohm's law. So we can simply substitute this in, right? So we're going to solve power equals voltage times current, but instead of voltage, we're going to replace it or substitute it with IR from Ohm's law, and we're left with power is I squared times resistance, current squared times resistance, right? Another way we can do it, we can substitute the current out of the power equation, right? Current is equal to V over R. So if we substitute that in, V over R, into our power equation for current, we get V squared over R. So the power dissipated in a resistance can be calculated if you only know voltage and current, or if you only know current and resistance, or if you only know voltage and resistance. So as long as you have 2 out of the 3, you can calculate power using one of those 3 formulas. Got voltage and current, current squared times resistance, voltage squared times or divided by resistance. A good Harry Potter quote. Okay, so we got power in watts. Now we're moving to total energy, right? So energy needs to be just in joules. So we're going to have to take our power, power, which is joules per second, V times I, and we're going to have to multiply it by time, because this would give us joules per second. We're looking for total energy. We want to get rid of the second by multiplying by time, right? So our second will cancel out, and we're left with total energy in joules. So the total energy transformed by a lamp is its power in watts or joules per second, multiplied by the time that the lamp is on. So we need to have the power consumed from voltage and current, our power formula, and we're going to multiply it by how long that's actually running, right? So energy transformed, right? What we mean by transformed, we're not actually just destroying energy, because we need to have conservation of energy for the universe to be happy. So we're transforming energy from its electrical energy into some other form. If it's a lamp, into heat and light, right? If it's a motor or a generator or something, right? We can convert it into other forms like kinetic or gravitational potential. Okay, but all of that's measured in joules, and we're just transforming from electrical, or really from chemical from the battery, to electrical, then to our useful form of energy. And it's found using voltage, current, and the time that it's actually running for. That's it for today. We're going to get into some crazy stuff next time. Here's a little sample. Lots of systems of equations, crazy hard math. Be ready for it. It's the trickiest part of the unit, if I do say so myself, and it will require your best math brains. So rest up, work on finishing up those resistance homework questions and the Google quiz. And I'll talk to you guys later. Let me know if you have any questions. Bye.